And
Yes.
can you see my slides?
The slides are working.
Good morning, everybody, and thank you very much indeed for inviting me to present to you. I represent the Medical Research Council unit in the Gambia, and I'm going to talk to you about nutrition and developmental origins of healthy aging. First of all, giving you a general description of the field and theory, and then I will move on to some exciting work that we are ourselves doing. I live and work here in the middle of the Gambia, and I was on my way to come to the conference when unfortunately my mother was taken a little ill. She's fine, but it made me have to present remotely, for which I apologize. So the theory we're going to talk about today is often called the developmental origins of health and disease, or DOHA. And what this articulates is that environmental conditions in early life have permanent effects on the body's structure and metabolism, and thus on an individual's later and risk of disease. The first evidence, perhaps, for this was published, the first human evidence was published here, although there had been lots of animal evidence from wartime studies by McCants and Widdowson, but this is some of the first human evidence. And this shows a correlation between infant mortality rates at the end of the 19th century and the beginning of the 20th century, and deaths from atherosclerosis in older people. You can see that there's a graphic correlation. It said that growing up in poverty causes some sort of permanent damage, perhaps due to a nutritional deficit, which left people with a lifelong vulnerability to aspects of affluent adult lifestyles, such as a high-fat diet. A similar sort of analysis was done by this gentleman here, David Barker. And on the left-hand side, we see coronary heart disease death rates from 1968 to 78. And on the right-hand side, a similar map of England showing infant mortality 70 years previous. Sorry, I'm getting a lot of background noise. I don't know if you could mute your microphone. And there was a persuasive geographical similarity between those associations. Now, of course, there could have been many other things that were confounding, but so this then required some detailed, more physiological than epidemiological research. And David Barker and his team were fortunate to find some very old handwritten records in Hertfordshire that had been recorded by this amazing midwife between 1911 and 1949. And they were able to follow up the people for whom we had exact details of their birth weights and then study them in later life. And what they found was that there was a persuasive association in both men and women, between the person's birth weight that had been recorded by this midwife and later outcomes in terms of cardiovascular disease mortality. And it's important to see that this is somewhat of a continuous association rather than just affecting babies at low birth weight. They found similar results in terms of hypertension, type 2 diabetes, and metabolic syndrome. And you can see in each of those cases, particularly for the type 2 diabetes and metabolic syndrome, again, there's this strong, rather linear association between birth weight and later health outcomes measured 61 to 70 years later. This was initially called, and still often is called, the Barker hypothesis, but I think it really requires another term now, the Barker theory, because it's been well proven and replicated in many other cohorts worldwide. So here's data from the USA showing the association between hypertension on the left and diabetes on the right with birth weight. So there have subsequent physiological measurements looking at fast cortisol, for instance, time reaction.
Dr. Prentice, you have to press share on your computer for us to see your slides.
Have you not been seeing my slides?
You are the host, then you have to press share.
I have been sharing. Can you see them now?
Yes, yes, yes. Thank you.
Do I need to go back and start again? Rapidly. Hello?
No, please go ahead, Professor Prentice. We listen you during the first slides, and we are now at slide 10 on the video, so you can go ahead with the what you were talking about. Thank you.
Okay. So there is also an association between not only the birth weight, but subsequent infant growth. And you will see here that people who later developed type 2 diabetes tended to be born small, but then grow fast. So they crossed their centiles in early life, and it was those that gained weight that became type 2 diabetics. Now, this has been put together with a lot of other ancillary information. And the theory is that a mother's diet and nutrient stores, her mother's ability to mobilize and transport those nutrients, and of course the supply line to the fetus with issues around uterine blood flow and placental structure and function, can create a scenario where a mother is unable to supply the nutrients to satisfy fetal demand, causing fetal undernutrition. And this fetal undernutrition creates inadequate building blocks affecting, and we have evidence from animal studies that it affects the kidneys, the liver, the pancreas, muscle, fat and bone, brain, and the hypothalamic pituitary axis in terms of cortisol responses. And there's been good animal evidence in support of all of these different intermediate variables. And these come together when exposed in later life to lead to central obesity, hyperlipidemia and hypertension, insulin resistance, which then cause the disease outcomes of type 2 diabetes and coronary heart disease. Now, it's possible that these associations could have been caused by confounding. In other words, babies who have a low birth weight are living in an environment which would be similar to one that would be likely to cause adult disease. It's also possible that there may be genes that affect both associations. So perhaps there is a gene or a cluster of genes which causes low birth weight, and the same cluster of genes causes adult diabetes. And that is a competing hypothesis. However, as I have said, there have been animal studies and others which make it pretty conclusive that there is a direct association between fetal growth, size at birth, and later disease. The first of these is animal studies, which show that if we deplete a rat dam's dietary protein from 18% down to 6%, you can see an effect on the top right-hand side there on systolic blood pressure. and likewise on plasma glucose in the adult offspring of rats that have been protein depleted. So there's good animal evidence in support of this. There's also evidence from the Dutch hunger winter, which all of you, I'm sure, will be familiar with, when there was a period of starvation and the babies born during that period have been followed up. And what the Dutch famine studies show us is that there are effects on cardiovascular disease and diabetes, microalbuminuria, and insulin secretion, and many other variables which seem to be associated with that very strict dietary restriction during the time of the Dutch famine. Now, it's also true that it's not just small babies that may be affected, but there's a U-shaped association, and gestational diabetes leading to macrosomic, fetally overnourished babies also have later life effects. And that's best shown in this HAPO follow-up study of a large number of children, which shows that the children of mothers with gestational diabetes also have numerous adverse outcomes, including insulin, impaired glucose tolerance, and others. Now, a big question here is, if you have been born small, is your disease completely determined, or is it in fact one of many susceptibility factors? And what we believe is the following, that the early programming of the susceptible phenotype, e.g. insulin resistance, interacts with later life course habits, e.g. weight gain, to cause the diabetes. So it is the life course habits, the lifetime habits, which are important in revealing disease for which there has been an early life susceptibility. And that's important in terms of what we'll say at the very end of this talk. And here we can see some of the data to show this interaction. So here's data with the adult body mass index on the x-axis and the proportion with impaired glucose tolerance or diabetes on the right-hand axis. And you can see that in low birth weight babies, there's a steep increase as you get fatter during adult life. In the average weight babies, somewhat of a lesser increase. And in the high birth weight babies, they're relatively protected from later life weight gain. One more slide to show this is an important one here. Comparing the odds ratio of type 2 diabetes compared to the reference indicated by the green circle there of normal weight babies, mid-range babies who have a lot of healthy, unhealthy lifestyles, then what we see is that there is an association with birth weight across all these 4 categories of unhealthy lifestyle. But very importantly, to show you that it is actually the lifestyle, if you look at the bottom right-hand red rectangle, those groups are very well protected from later type 2 diabetes, irrespective of their birth weight. So keep this in mind. Everything is not lost if you have been born a small baby. So that, and I really apologize for the fact that you hadn't seen the earlier slides due to our technical hitches, that is a summary of the evidence we have so far linking fetal malnutrition, low birth weight, and later life disease. And as I've mentioned, there are various theories as to how this linkage could occur from the early exposure to later disease. I want to end my presentation by showing you some very exciting data that we've got from our field studies in the Gambia, looking at this issue of epigenetic programming. So another hypothesis is that something happening very early in life has changed the methylome of the baby, its epigenome, and possibly other issues such as microRNAs, to have a lifelong susceptibility to later disease. So let me quickly show you what we've done in this domain. This work started with animal studies, and these are the poster boys of epigenetics, the agouti mice. These two mice are sisters, they're from the same littermate, and the phenotype has been altered by the mother's, can be altered by the mother's diet before conception. This is well known for the agouti mouse with the ectopic expression of the agouti allele, which causes the mouse to become yellow, fat, and diabetic. But the question was, does this occur in humans? And we were very fortunate to be able to use an experiment of nature to ask this question, because we have a very long and prolonged dry season in the Gambia, shown on the left, and a rainy season on the right-hand side. And this has a profound effect on what people eat. And we were able to interrogate this in terms of variables that have happened in the very early life of the embryo. For reasons which are complicated, and I won't take time explaining now, we're able to, by studying so-called metastable epialleles, we're able to predict that the changes we're looking at have occurred before day 9 in a human pregnancy. So we're talking very early on in the baby's development, before gastrulation occurs. And that means that we're looking at the nutrition that has occurred prior to pregnancy. We're looking at how nutrition might affect the development of the sperm and the development of the egg that come together to create a new embryo. And so I want to emphasize in your mind that the nutrition we're talking about is preconceptional and periconceptional. Now, methylation, the form of epigenetics that I'm going to talk about now, is very nutrient hungry. All of those boxes here in yellow with a red outline are nutritional inputs, and they are required in order to produce the methyl groups in red at the bottom left that are added to the DNA in order to regulate the expression of genes. On the right-hand side, you can see a heat map of 170 mothers who were studied early in conception, and you can see that in the dry season on the left or the rainy season on the right, there are profound differences in the patterns of all of these nutrients. And what we found, and this is our latest publication on this, but we have replicated this many, many times now, is that if you know where to look, and you look at these metastable epialleles in the red here, then there is a very strong effect on the percent methylation according to the season, the month of birth, the month of conception of the baby. And that's also shown here with a different set of data, that this graph now shows the peak methylation, and the left hand, there's 3 different data sets here, Enid, later kids, and emphasis. And what I'm showing is the metastable epialleles in red, and then what we call season of conception CPGs, but others that aren't metastable epialleles but are still seasonally sensitive. And you will see by those violin plots that the peak of methylation occurs in babies that are conceived in August, September, October, to such an extent that by taking the DNA of a child, we can pretty much tell you which month it is born in. So this is a very, very strong effect. And the question is, so what we've shown then is that diet affects methylation. And the next question is to ask, well, does this matter? Is there any phenotype or health outcome associated with this? And because time is short, I'll just show you 2 of our recent publications. The first is that we've found a very strong association between methylation at the gene PAX8 and thyroid function in children, and we predict that this would have an effect into adulthood. We can show associations with thyroid size, with free T4 levels, and with body mass index and bone. So this is the first of the indications that, yes, these things are really going to matter. The second example is in relation to obesity, whereas in fact we've done much much more research on this in this domain, and looking at the pro-opiomelanocortin region gene, where there are some sensitive CPGs that seem to have a strong effect on susceptibility to obesity. We published this in a number of different papers, and you can see on the bottom left a patient who has had a profound change in the epigenetic rather than genetic patterning on the POMC region. And putting this all together, what we hypothesize is that this has evolved, this and the other sensitive areas have evolved as means by which the body, the organism, can sense the environment into which that conception has occurred. So in this case, increased POMC methylation during the hungry season. This then decreases POMC expression and reduces the satiety response to food intake. So the organism has sensed, it's then adapted, and then it has responded. Because if you've got a low satiety response, then you're going to be likely to overeat and become obese. So this sense, record, adapt, respond is the hypothesis that we believe is true for many of the regions that we are studying. So I think this is an exciting new domain. The big question, of course, is if we can understand all this, can we then recommend to mothers or indeed give them supplements in the periconceptional period, which would break the intergenerational cycles of later ill health? Let me end by summarizing some of this and asking the question, what does this matter in terms of prevention of adult chronic disease? And I think the best way to understand it is that, of course, life interventions, late interventions, will help vulnerable individuals, those that have had a low birth weight or fetal undernutrition. But really importantly, if we knew how to, and if we could intervene very early in life, right from the preconceptional period, then it really offers the potential to achieve larger effects, would improve functional capacity, improve health outcomes, and may well benefit the next generation as well. So in summary, fetal undernutrition has a very profound effect on lifelong health, which is most exposed in later life and most exposed if you live a unhealthy lifestyle, which leads to inactivity, overconsumption, and obesity. But that interventions are still possible, and that if we could intervene both in later life and in the early period, then we would get a more positive, a double achievement in terms of health outcomes. So I thank you very much, with repeated apologies for the glitches at the beginning of this and for the fact that I'm not with you personally.